I'm working the Elmos Institute of Freiberg, and also I work between the Elmos Institute of Freiberg and the Center of Advanced System Understanding in Germany. So, I conduct some projects about autonomous systems, more specifically for aerial vehicles. So, for now, 1 year that I'm working on how to build a set of autonomous vehicle which perform some missions without human assistance. So from this experience, I will show you what are the main challenges that we face when we want to build some autonomous programs to perform some mission without the human assistance. And I will take the opportunity to present the concept of and the design of self-organized autonomous swarm that I'm working on. So, my presentation will turn about this point. First of all, we will discuss about the main challenge that we need to understand to face the problem of the swarming. And we will also discuss about the communication protocol problems and how we can distribute the tasks. That is another challenge that we have when you want to build a drone program. And we have the problem of consensus controls. So by consensus control is about how to regulate the action performed by the drones to achieve some tasks which contribute to the advancement of the missions. And we will also discuss about the resilience of the swarms and what happens when one drone in the system fails. And I will show you some experimental results that highlight the impact of using the concept of swarming. So, for my presentation, I will first start by stating the problem of swarming. I will explain the main challenge of my project and what are the challenges that we have to face when we want to build an autonomous swarm, and what are the skills that we need to tackle some challenge that we have. And we will discuss about some background that we need to understand before implementing a dedicated project, especially the ecosystem of autonomous swarms and the different kind of vehicle that we have in autonomous, and how the type of vehicle can affect the communication between each drone inside the swarms. And in the second part, I will present the concept and design of my proposals. It will be first about the formalism of the swarm concept, and I will present the architecture that I have implemented. And we have some swarm daemon that we have in our architecture that we use to regulate the collaboration and the cooperation between every kind of drone that we have in the swarm. And we also discuss about the concept of consensus that we use to regulate the action that the drone will perform to achieve some mission. And for the proof of concept, we have some tests of simulation, and we'll present also some results and some video that we have recently from a real test deployment. So we'll start now with the problem statement. Here I will show you the problem that we have when we talk about the concept of swarming and what are the main challenges that we'll face and how to solve the problem that we face in the swarming concept. So the goal of the swarming is to firstly build a fleet of autonomous vehicles which perform some tasks in coordinate manner to achieve the common missions. And one important thing is that the drone will perform some tasks in collaborative, and we have a concept of cooperation. We have a concept of they will share some resource, and they will make some communications to achieve the missions. So for that, we have to distribute the tasks around a fleet of drones. So, and we will have the drone, they will work simultaneously to achieve some common missions. And we have another concept that is about the hierarchical, we have to hierarchical set the swarms so that we will have one drone that will be used as the masters, and the wolf, the rest of the drone will work as a worker. So the master sometimes that we use is a big drone, or it can be sometimes if a fixed wing drone that will have a high altitude, and based on this altitude, you will get a global overview of the wolf environment, and it will assign some tasks to every kind of drone that we have. So this is another challenge that we have here. So how to build a hierarchical level when we have every kind of drone based on the responsibility that will achieve some tasks. And so the added value of this concept is that firstly, we will fly too quickly, and we achieve the mission in some little time, because they work together to achieve some little tasks that can work in the coordinate manner. And we have a quick exploration of large area. And by using this concept, we can also collect lots of data sets, because we have a fleet of drones that we can use to acquire data sets in real time. So this is a simple example that highlights the impact of the swarming concept. So we make that here. Is it an example of the survey mission that we will use to survey an area of 1 kilometer square for hyperspectral imaging processing. By using the conventional approach with a single swarm drones, we achieved this mission in 2 days. And don't forget that every time we have to make some little downtime to change and recharge the drone batteries. So in this case, we can say that this approach is not almost good, because it takes more time, and the computation is made sequentially until we cover the wolf area. So when we use the swarming concept, by using the swarming concept, and we use a fleet of worker drones which work together to achieve a common missions, we achieve this mission in 2 hours. So from 2 days, we switch to 2 hours. And the drone flies simultaneously, and we can acquire lots of data sets in real time. And so this approach is very interesting, because by using this concept, we can explore some big area in some record time. But we have a lot of challenge and constraint that we have to face when we work on the concept of autonomous swarming. The first one is about the technical barrier. And don't forget that when we use drone, our drone that we have currently are a limited flight time, because the battery life cycle place is too short, and every time we have to change and recharge the battery. This affects the timing. Another one is about the interoperability. Since that in the swarm, don't forget that we can have different kind of drones with different kind of communication protocols. So the question is that how to create a mesh communication protocol, and to let the drone communicate if they have a different communication protocols. And we have also the problem of mobility. In the swarm, sometimes when one drone moves too far away from another one, we can lose the communication. So we have to maintain a certain distance that prevents the network stability. And another challenge is about the embedded intelligences. So by the intelligences, we talk about how the drone reacts, how the drone collaborates, and how the drone coordinates some job or tasks with another drone to achieve the common missions. And what happens when one drone in the swarm is breakdown? How the system reacts? And we have the consensus control that we have to define to regulate the action performed by the drone to prevent some bad actions. Because every bad action will affect the state of another drone that we have in the swarm. And together, the drone, the swarm, in the swarm, every drone must detect some bad event like collision or crash that we have. And another problem is that since we use the concept of swarming, and we have a multi-source of data set that we can collect in real time. And the size of the data set is very large to process with the conventional processing that we have in background. So how we can implement a dedicated system which can achieve the data set and process the data set in real time. And don't forget that the data set, the size of the data set sometimes is big. Sometimes can be for data set from RGB, for camera, etc., that we have to process in real time and send the feedback result to the drone to react. We have some constraints, not technical challenge, but is very important because sometimes it affects the deployment of a project. Is it about the ethic of the use of the drones? And we know that the regulation about the use of a drone in civilian area is a little bit complicated because sometimes it depends on the kind of the drones, of the type of emissions, of the area that we have to cover. And by using the swarming concept, sometimes the regulation can differ from one drone to another one. And we have another constraint related to the weather and the environment condition, which can affect the network stability and the GPS signal. So to face with some challenge regarding this swarming concept, we need first to have some skills in robotics, especially so in the design, the conception of the drones, and how to implement some automatic process for the data acquisition, etc. We have the intelligences concept to build an intelligent drone, we have to understand some concept related to multi-agent system. When we can consider a swarm has a multi-agent, when one agent can work as can have some action that will be regulated by the agent concept that we have. We have a learning concept, so the machine learning approach will be very useful if we want to embed the learning concept to let the drone learn about some complex phenomenon. And to face the problem of the data set, I recommend to use the big data concept because with this, we can achieve a lot of data set. We can process any kind of data set regarding the structure, the type, and it's very fast by using this concept. We also have high-performance computing skills that we need because now the mission that we will perform on the drone is not a sequential mission. It will be distributed around different kind of drones. So we have to have a background about the parallelism, the distribution concept, and the high performance computing of some tasks related to the drones. And we have some other skills that will be sometimes useful, like Linux, understanding the virtualization and networking, because we will have to build the communication architecture. And sometimes the formal verification skills will be helpful if you want to test if our system is in good ability. So, with our research institute, we have 8 drones, and most of them are multi-rotor. And for the moment, I perform some tests with the nano drones. It's 4 drones. I use one as a as a master, and the 3 one will serve as a worker. And when I'm sure with the test, I'll deploy this on the big drones. And we want also to build a coordinated ground-to-air program, which will allow us to have a full coordinated from the ground to the air between a given drone. And so we plan to add the dogbot inside our swarm to perform some other collaborations. And so this is one example of our last implementation that we have. First one, the big drone will fly at a given altitude. It will search one target, and it will send this position to the dogbot, and the dogbot will move to this target. It will identify the target, and also it will see from the identification that it have, it will tell the drones, okay, so now I have some information about the target. Come here and pick up the target and move to another positions. So this is another project that we plan to work, and we will integrate the dogbot in the swarm. So there is not a big difference, except that for the dogbot, we don't have to consider the Z position, because for the drone, sometimes is it about X, Y, Z, and for the dogbot, it will be just with the X and the Y. For the software tool, we opt for most of the time open tools. We use Rust as a programming framework, and we use the standard MAVLink protocols. And here we use Linux 20.4, yes, for the implementation of the world program, and the Raspberry Pi is the operating system of our drone that we have. And to perform some simulation, sometime before deploy on the real drone, we perform some simulation. For that, we use Gazebo 11 with RVs to have some information about the perception of each drone. And sometimes we use a MavProxy. Is it a light version of ground stations? And the drone that we use in Gazebo is under the Autopilot architecture. For the real test, we use Autopilot, and sometimes QGround control to sometimes coordinate or control the swarm that we have. So, okay, so before we go to the conception, it's very important to understand some information about the communication architecture and the communication protocol. And because it's very different to the classical drone concept that we use. The first one that we need to understand about the swarming concept is that in the swarming concept, we have a set of drones which work together to achieve a certain mission, and we have some interaction. The first one in the architecture is that we have a fleet of drones. It could be autonomous or not autonomous. So when is it an autonomous drone? Is it about the drone that would not need the human assistance? So for not autonomous, sometimes it's about the drone that is remotely controlled by a human from the ground. And the set of drones will form the multi-UAV, also called swarm. And we have the environment. So in the swarming concept, the definition of the environment is very important because each drone, based on the local environment that it has, it will perform some action in this local environment that it has. And we have a perception. So the perception is about the information that the drone will collect from the sensor, embedded sensor that we have. And another interesting point is the waypoint that the drone will follow to create the path planning. So here we have to go to understand, because here it's very important about the waypoint, because two drones can share the same waypoint. And we have to be careful because sometimes if two drones share the same waypoint, we can have some problem of a collision, of a crash in the same point. And also we have intra-UAV communications, because the drone will communicate with another one. So we have intra-communication, and we have some communication from the air to the ground. It will be between the ground station and the drone flying the swarm. And we have different types of drones, and this is also important because if the kind of drone that we have in the swarm will determine if is it an autonomous or if is it an homogeneous swarms or heterogeneous swarms. So in homogeneous swarms, sometimes is when all drones in the swarm has the same configurations. But if is it a heterogeneous swarm is when in the swarm we have different kind of drones. So we have 4 kind of drones. The first one is about the helicopter drone that we have. It contains a single rotor. So this kind of drone has a limited mobility, and because it just have a single thing. But we have some another advantage that like the flight time, and it can hold the same position from a certain from a certain time. We have a multi-rotor that is sometimes an improvement version of a single rotor, except that this drone has a limited flight time because of the battery life cycle. We have a fixed wing. Is it another version of the drones that use a fixed wing attached to the structure of the drones, and it flies for a long time, and it has a high velocity. But the problem is that it cannot hold the same. It cannot hold in the same position for a long time. The last one is the hybrid drones. It takes advantage from the multi-rotor and the fixed wing rotor to face some challenge some problem that we have here. So when we build a swarm, it's very important to understand what kind of drone we have, because it will really affect the mobility of the swarm. It sometimes affects the mission planning, because if we have one drone with a limited flight time and another one with a long flight time, we have to be careful about the workload of the drones. And so for the communication architecture, we have different kind of communication architecture. Here I have made a classification of the communication architecture. So the first one is a centralized communication architecture, and we have a decentralized communication architecture. And from the decentralized communication architecture, we have a single group of architecture that we have, and we have another one like a multi-group that is an extended version of a single group. And don't forget that the communication architecture of a drone is belong a flying ad hoc network. It's dedicated for a mobile object which belong a manet. So if we want to build a Wolf autonomous system which embeds sometime all kind of vehicles, it's very important to understand the communication protocol that we have between the FANET and the manet. And if we want to switch from the vehicle to the aerial vehicle to the mobile vehicle, it's very important that we have to cross the protocol to allow easy communication. So I will now explain the different kind of communication architecture, because with this communication architecture that we will implement the kind of mission that we have. The first one is for the centralized communication architecture. With the centralized communication architecture, all drones will communicate directly with the QGround control stations. And that we don't have a direct communication between drone to drones. All communication between two drones must pass through the QGround controls. This is another problem because if we are connected to the QGround control station, we are not allowed to move too far to the QGround because we lost the communications. And so in this case, we can see that this kind of architecture has some weak points. The first one is about the coverage space. We use this sometimes to cover a limited environment because we are not allowed to go too far to the ground control station because we will lose the communication. Another problem is about the interoperability. For this, all drones in this kind of architecture must have the same protocol to enable communications. And another one is the single point of flight. If the QGround control is down, we will lose the communication from the world systems. This is why we switch here to the single, the decentralized version. So the decentralized version is an extension version of centralized communication from. We have to remove the QGround control dependencies. So with the decentralized version, the first one is the single group. And in the single group communications, we have three kinds of actors here. The first one is the QGround. We have another drone called the gateway drones. And we have the rest of the drone in the swarm that we will have to use for the communications. All communication between the QGround controls and the rest of the swarm pass through the gateway drones. It will relay the information from the QGround and dispatch this to the rest of the drones. It's very important to understand this because with this kind of communication, some of the swarm concept that we have now is based on this type of communication architecture. And in this, we have the communication is based on the intra-communication that we have. We have three kinds of intra-communication. The first one is about the ring topologies. And in this topology, we make that every drone can serve as a gateway. We can switch from one drone to another one to relay the information. So in this case, the information is always available. And we have to ensure the fault tolerances that if this drone is off, we can switch to another one. But the problem is that it's very difficult to scale to add another drone because we have to reboot every time the network when we want to add another drone. The second one is the star topology. With the star topology is used to face the problem that we have there. And in the star topology, we have a drone that will connect all another drones, and it's very easy to add another drone in the topology because we have just to connect this to the gateway drones. But the problem is that since the information is centralized to the gateway drones, if this drone is off, we lost all communication that we have there. So the last one is the best, I think, is the mesh topology. It takes advantage of the two proposals, and it combines the availability, and it faces the problem of fault tolerance, and that it allows to add any drone in the swarm easily. But here we have some weak points that with this kind of communication architecture, we cannot also move too far from another one drone because we will lose the communication. So this is why this architecture is used for limited coverage. And we also have a problem of interoperability. All drones inside the swarm must share the same protocols. We have another communication protocol is an extended version of the single communication from the single to multi-group. Yes, it's a little bit different. We have to build a set of different groups, and in each group we have a gateway that will serve as it will relay information between all the drones in the same group. And the communication between two different groups of drones will pass through the ground control stations. And it presents a single point of fire in the ground control station first, because if the ground control station is off, we will lose all communication with the swarm. And if one gateway in the given group is off, we will lose the communication inside this kind of group. The last one is the multi-level architecture. The multi-level architecture is, for the moment, the best communication architecture that we have for the swarming. And with this kind of communication architecture, we don't have a problem about the single point of fire, and we can use different kind of drone to perform the swarming concept. And it consists of 3 layers. The first layer is the involved communication between drones. The second layer involves communication between group of inside the drone. And the last one is to involve communication between the group of drone and the ground control station. And for this, we use the group of drone that is very close to the ground control station, and will replicate the communication to another one. And another advantage is that we can perform different kind of mission. For example, with the group, this group of drone can perform coverage, swarming survey missions, and this one can be used for object detection, etc. So it depends. So now we will start with the concept and design. I will show you the concept and design of the swarming that we have performing with my research institute. First of all, the proposed concept is based on different kind of methodology for the communication. To address the problem of communication, we use a decentralized communication architecture. And so, why? Because it allows us to eliminate the dependencies from the ground control station. And we want to build a full autonomous drones, a full autonomous swarm of that will perform some action without the human assistance. And why we opt for the decentralized architecture? Because with this approach, we can extend from different kind of communication architecture depending of kind of the mission and the purpose that we want to have. And for the self-organization of the swarm, we opt for the leader-follow pattern. The leader-follow pattern means that in the swarm, we have one drone that will serve as the master, and the rest of the swarm, the drone inside the rest of the swarm will serve as the worker. And the master drone is the main coordinator. It coordinates the action in the swarm, it sends the mission, and sometimes it receives information about the progress of the mission inside the swarm. While the worker will work as a pure worker that will execute the tasks received from the master. And we have a concept of quorum election, which means that in the swarm, for the election of the master, we have to make some quorum election process. And for the intelligence, we use the multi-agent system because it allows us to consider a drone as a modal reflex. And we make that with this concept, we can perform some actions, and every drone will have a perception. It will make send some message and communicate with another one. And we have action performed by some drone will affect the state of another drone in the swarm. So now to build an autonomous system, the first one, we need to make the area decompositions. By area decomposition, it means that we have to understand the environment assessment, and then we will fix the number of drone that we will use depending on the environment that we have. And so, if we have a fleet of homogeneous drones, we will opt for the partition based on the shape of the environment. It means that we have to split the environment under the same size. But if it depends, it is not homogeneous, it could be heterogeneous, we will opt for the densities. The density means that we have some area which contain more information than another area, so it will be used to dispatch the workload. And after that, we now opt for the mission planning. For the mission planning, we have to assess the mission so that it will be distributed inside the fleet of the drone, so that each drone will perform its mission that it receives and send the information to the master drone to have a global information about the investment of the missions. And to perform this kind, we need to understand the concept of message passing. We built a distributed mission planning for the message passing interface that we have. And this is very important about which kind of message passing we will opt for the swarming concept. And the last one is about the consensus control. It will be used to regulate the action performed by the drone to move and to work together in order to achieve a common mission. For the area partitioning, is about we have to split the area under sub-area, and we affect each sub-region to one drone. And we have to create a boundary to avoid some collision, because we have to collaborate about the coordination when we move to the boundary of the sub-region. And don't forget also that sometimes it depends on the altitude that we have in the swarm. If the swarm the drone has a big altitude, sometimes it affects the partitioning, or sometimes it affects the area of each sub-region. The second step is about the distribution of the tasks. So we consider that a mission is a set of jobs, and we take the job, we split the job under tasks, and we assign this to each, we allocate each processor in each drone to compute the tasks that it receives. And in this manner, it allows us to reduce the time complexity of the mission by the number of the drone that we have inside this one. And to perform this action, we want to be sure that we have some available core processor. In our case, we use one core processor for one task that will be executed by one drone. And concerning the message passing, we have two kinds of message passing pattern. The first one is about the synchronous communication message pattern, and the second one is for asynchronous communications. So it depends on the kind of mission that we have. If in your mission, is it a mission that involves real-time reaction between the drones, we opt for asynchronous communications. Or if is it a mission that, in this mission, we don't have a real-time interaction between the drone, or sometimes we have to wait until another drone achieves its task before go away. So we will opt for the asynchronous time delay. With the synchronous communications, all drones must publish and subscribe the topics, services in the same time. While for the asynchronous time delay, we split the communication time under different kind of round. And from each round, only one drone is allowed to publish and subscribe to a given topic or services. And we repeat the same process until we reach all the drones in this one. So the first one is good because we have a real-time interaction, but sometimes we have some collision about the message that we share if the drone will use the same communication channel. For the second one, is not synchronous, is not dedicated for real-time communication, but we are sure that we will not face the problem of package, of loose package. And for the consensus control, we define the consensus control as a communication graph. So in this communication graph, it allows us to have an overview about the interaction between each drone inside the swarm. And every time one drone performs one action, it could affect the state of another one. And we have two kinds of states. We have a bad state and the good state. Bad state means that is it a state that will not contribute to the advancement of missions. But the good state is some state performing from the good action performed by the drone to go together toward the goal missions. So it's very important because to understand the concept of consensus control, because it allows us to regulate the action performed by the drone. And so in the implementation, every time we have to return a feedback result as a Boolean value. That means that true is for good actions, and 0 means that we don't finish with in the good conditions. And to continue, every drone will take as input the state of the wolf drones inside the swarms, and it will match the state of all drone with its given state. If the value is positive, is true, it means that we can continue to compute the missions. Otherwise, we will stay until we repeat the same process. And we reach a good consensus when, during every time, we move together the common state. The final state means that at the last for the last round, all drones must be in the same state that will be the desired state that we want to reach. So now for the proposed architecture, we have here, is it a multi-layer architecture? And we can extend this by adding some another architectures. So for the moment, is it a two-layer architecture? So the first one is based on Autopilot, and we have, in this architecture, we have two different sub-layers. The first layer is for the logical implementations. It contains some services and commands that we need to embed Swarm programs. And so before perform some tests on real drone, we have given sub-layer that we use sometimes for the simulation. And the second layer is about the distributed computation layers. So this layer is used especially for the computation to compute the distributed mission inside the swarm. It's based on Rust, and the architecture, the communication architecture is a single group communication architecture. We'll make that we have here the Wolf drone that is connected to a single leader drones that will serve as a gateway which will relay information between the application layer and the distributed computations. And for the communication protocol, we use a MAVLink, the standard version of MAVLink, to enable communication between our two layers. And we also make that for the intelligences here, and we use here the leader-follow patterns. It means that in the leader-follow pattern, we have one drone will serve as a leader. It will be responsive of the management of the swarm, as well as the achievement of the missions. And we also have the follower drones that will work as a worker. So this kind of drone is just used for the computation of the missions. And so what happens when the leader drones break down? To avoid this problem, we use a standby leader. The standby leader role is to work when the leader is down. And by default, it receives some feedback information from the leader about the health status of these drones, and it performs some checkpoints about the advancement of the mission and the health of the drones, so that if this drone is off, automatically it will switch for the continuance of the mission planning. And the services that we exchange inside the swarm is based on the service trade poles. It means that we use different queue to achieve the services that we have to complete. So for each services, we use two trades. One for the request that will be used to process the request, and another one that we use for the response. And the communication service between the follower drones is performing in synchronous manner, so that we have a real-time interaction and allow us to share some resource or coordinate some action in real time. While for the leader drones, it is made in asynchronous manner, because we don't need every time to communicate with the standby leader. And the standby leader receives information on demand of the leaders if he asks him to send some information about its health status, etc. And so now, is it about how to control the swarm consensus? So to control the swarm consensus, we use three kinds of daemon. The first daemon is the swarm manager. Is located on the leader, and it consists of two components. The first one is the mission component, and the role of the mission component is just to plan the distributed mission. By planning the distributed missions, it means that it shares the tasks to different ROS core inside the follower drones. And we have the mission manager component. This is used to perform some tracking tasks about the advancement of the missions, and is also used to receive some information about the health status of the worker drones. And by the same time, it performs some checkpoint about the advancement of the mission and about the status of the main drones. It sends this information to the standby leaders. We have a drone manager daemons. This daemon is located on the follower drones, and it consists also of two components. The first one is the task manager, and with the task manager, it just uses it to assign each task received from the master drone to the raw score. And don't forget that by the raw score here, is it a set of CPU, RAM, and SDK that we have to process the information. So, from the information received from the swarm manager, the task manager component will make some assignments so that each task will be assigned to one raw score to perform the task. And the last one is the standby swarm manager. Is almost the same. It has the same role like the swarm manager, except that is it in inactive mode when the swarm manager continues to work. So this is why it will receive every time some information about the health status of leader drones, and it performs some checkpoints. And this daemon is used for the continuity of the activity in case that the main drones is breakdown. So, here is it about the communication process that we have between the leader drone and the standby leaders. How the two drones communicate to coordinate and to face the problem of fault tolerance. Fault tolerance means that if in the system the main drone is off, we must continue to perform the activities. So that for the first one, the leader drones will submit every time recurrently he submits a head beef to the standby leader to notify that is always working. And it also submits a health status about the level of the batteries and some another information that will be useful to determine if this drone could also use the main leaders. And by the same time, it performs a checkpoint. The checkpoint is very important for the continuity of the activity because if this drone fails, the second drone will access to the checkpoint file, and based on the information stored here, it will continue the activities without require some information from the main drones. And so we switch from standby to active when the standby leader detects a bad diagnostic from the main leaders, or sometimes when it does not receive a head beep from the main leaders, or if we have in the share file, we detect a collision from the leaders. It will automatically pass from standby to active mode to achieve and have the business continuity of the swarm mission. And here is about how we schedule some job that file from some drone that is breakdown. So to perform this action, we use the FIFO and priority classifier. By FIFO, it means that the first drones which file will be the first drone that we will plan its task. And we have a priority order because don't forget that by the swarming concept, we have different kind of job that we will perform in the same time. So we have to give a different priority to each kind of drones. So we have three kinds of priority. The first one is about the highest priority. Is it about, it contains the task that is very useful from the swarm management. And we have a middle priority. Sometimes middle priority is some job that is not necessary. We don't necessarily use this for the advancement of the missions. And the last one is some optional jobs. So it could be a collision avoidance job, etc. And for the environment, we build here a dedicated integrated environment that is used easily to implement a Swarm project. The first one, we have Gazebo directory. We organize our workspace so that we have here some scripts that we use to launch some different kind of drone. And we have the world contain any information about the environment of Gazebo and the model that we'll use to build the world. We also have another directory that contains all dependencies and drivers that allow the communications and the interaction between the MAVLink and the ROS communications. And we have the last directory that is the source directory that is very important. Is it the heart of the workspace? It contains some information about the code that we use. Here we make that we have some file that we use to include some dependencies package that will be useful for our project. And we have a dedicated directory to launch our Swarm, and we have some customized directory for different kind of message and services and action that we'll perform in the swarming. This is very important because with the current workspace that we have, it's very difficult every time to build a Swarm concept. We have to go in some directory or some file to rechange, and it takes more time. So now we'll go with the experimental test. So for the experimental test, for the moment, we have different kind of tests. We have a test for SLAM, and we have two kinds of SLAM. We use some tests for visual SLAM and SLAM with LiDAR. And we also use this for the RT algorithm to explore some unknown environment by the concept of swarming. We use this also for point cloud generation for large environments, and we use for multi-target detection. It means that based on the given area, we will split the area under sub-region, and one drone will work on its sub-area to detect different kind of targets. And we have a distributed covariate path planning algorithm that I will show some experimental tests. For the experimental test, we use here a 5 UAV swarm. We use one as a leader, and the fourth will serve as a follower. And each drone is equipped with 2 batteries. And the perception of each drone is about 2 meters square, and it flies at a 5 meter altitude. We perform some tests from a small area ranging from 400 meters square to 3 kilometers square. So the first experimental test is about a single UAV swarm. It means that in this experimental test, only one drone will play the both role of master and the follower in the same time. So this is our first autonomous flying. This drone will take off, it perform a complete rotation, and it lands in the same place. This is very important because it highlights that our system is, the formal verification our system is proved. It works well, and we will add some functionality in our ROS project. The second one is for the square coverage path planning algorithm with a single swarming concept. So it will perform a square for the path planning, and it will come in the same positions. In the next slide, we will distribute this. The main objective is to distribute these tasks to different kind of drones. So for the moment is just to show that this drone play also the role of the master and the follower also. This means that it coordinates its action, and always it sends some command to him to perform some action. And the last one is a project that an implementation of another single path of a covariate path planning algorithm for a single UAV on the big drones for a real work field. And so we use this to perform a concept of swarming with this area. We cover around 800 meters square with these drones. But after we will switch this program to different kind of drone. So for the moment, we work slowly, we test on every drone to avoid some problem. And it's always perform the back and forward path algorithm for the survey missions. And after, when he cover all the area, he will come to the same position. So this is a dedicated version of squad programs with a 3 UAV swarm. So we split the environment under 3 so that the wolf environment is assigned to one drone, and the one drone will perform its action so that it will perform the algorithm in coordinate manner with another drones. And they share the information about the boundary to avoid some collisions. And so we go together and they work, they coordinate. Every time that one drone moves to another waypoint, it shares its position to the wolf swarm, and the drone will use this to improve, to avoid some collisions. And another important thing is that with this concept, we also have a battery level. We consume less battery because the task is distributed across different sub-area. So here is it, we detect a collision. So the drone here, it stops slowly, and it anticipates on the next position to avoid the collision because it has some information about the next waypoint of the adjacent drone. This one is a coordinate motion planning that we use for the swarming. So is it about a 3 UAV swarm which work together to achieve, suppose that it could be a given mission. This highlights the importance of message passing. So each drone, before moving, it sends its next position to another adjacent drone, and the drone will use this to anticipate and avoid some collisions. And this communication is performing in synchronous manner, so that we have a real-time interaction, but we have some other kind of communication that we can implement, like the asynchronous manner if the mission does not require a real-time information. This is another one for the coverage back and forth survey with a 3 swarm. So we split the environment under sub-environment, and we assign one drone to one environment, so that each drone has a local perception of each sub-environment, and it will perform the CPP algorithm. For the moment, we have implemented around 12 covariate path, distributed covariate path algorithm, and it works very well, and the time complexity is reduced from exponential to linearity. And here we make that they move slowly to avoid some collisions. And so the collision avoidance depends on the consensus control that we implement. So is it a user-defined logic? So it depends on what kind of logic you want to implement to avoid some collision. And this is another experimental test that we perform on this paper. The author proposed the LMAT algorithm that is it a cover path algorithm that we use to for the survey mission is dedicated for drone with less batteries. And so when we apply the concept of the classical approach proposed by this author, we perform the swarming in 22 minutes. And so the drone will start there, and it will move. Every time it moves to the next point, it has to accelerate and decelerate until it reaches the final position, or until the area is completely covered. With our concept, we split this environment under sub-region, and we assign each one to one drones. And when we launch, we make that the time complexity decrease to 6 minutes. And here, every adjacent drone will share a waypoint, so that it's very important to share the boundary waypoint because it allows to avoid some collision and coordinate the motion of the drone when it is in this place. And we also remake that here we use less battery, and at the end of the flying time, we use just 0.5% of the batteries. But for the first one, we make that we finish with 0% for the 2 batteries by drones. So for the time complexity, we make that when we use the conventional approach by using a single drones, we make that the time complexity from the time complexity regarding the area that we cover will increase from linearity to exponentiality complexity. By using the concept of swarming, we make that it allows to reduce significantly the time complexity until we reach a linearity here. So every time we add a new drone, it improves the time complexity. And we make also that here we don't have a big difference. Don't have a big difference because it's just a little area. It's around 400 meters square. So we don't have to use 4 drones to survey on 400 meters square. We can say that the swarming concept is has a good result when we work in a large area. For the power consumption, we make also that swarming concept allows to reduce significantly the power consumption. The first, this graph represents the power consumption with just a swarm composite of just one drone. With just one drone, we start around with the 200%, and we will finish with 0% of the battery level. When we switch to 2 drones in the swarm, we just use just a battery level from just 1 battery. We have just to consume just a battery level from 1 battery. And it's very important because it allows us to save more energies when we plan for the swarming. And for long distance, it's almost the same. We make that for long distance, we cannot achieve a swarming concept with just a single drone because we'll consume the Wolf battery inside the swarm. But if we move to the swarming concept, it allows us to get some batteries because the task is distributed inside the swarm. Another one is about the network bandwidth. Yes. And if we opt for the swarming concept, it also has to decrease the network bandwidth by the number of UAV that we have, we add in the swarm. Here is the network bandwidth is reduced because we make that the task is distributed around inside the swarm, and every time we don't have to communicate with just one drone because lots of communication with one component will involve more network bandwidth that will produce. And for the network latencies, we make also that based on the proposed message passing pattern, in the two cases, we make that we have 0 package that we lost. And the time delay is between 20 milliseconds to 70 milliseconds. So, and if we evaluate from the literature review, is a very good result because most of the time delay is around the range of acceptability. And if the time delay is more bigger than 100 milliseconds, is not good. And for the ROS communications, the ROS communication graph here highlights the high availability of the swarm. And for the 4 follower drones, we make that the ROS communication show that here we have a full connected graph, so that if we have one information in these drones, we can access this information from another one because we have any edge from one node to another one. So we can access any services, any topic, or any action inside this one. This is very important because it shows that the system is highly available, and in case of fault tolerance, if this drone is not accessible, we can continue with another resource from another drones. So for more information about the concept of swarming, we have one publication in the MDPI journals. I suggest you to read this paper. We will have some more detailed information about the concept of swarming. And we also discussed about the architecture, also discussed about the challenge that we have and how to understand the distributed tasks in the swarm concept. So for our team, we work together both on the software part and the hardware part, but my concern is about the programming of the swarm concept. And I'm working on the dedicated API for ROS. It will be a distributed version of a ROS. It contains some API that allow to implement some sample missions. But in the future, we plan to add another functionality to improve the API that we have. And so if you are open for some future collaboration, we are open to receive some PhD student or master student or some company that would like to join us for the project. So thank you. Okay, so any question?
Can you talk a little bit more about the tasks that you were, in one of the slides you showed tasks being assigned to the different ROS nodes within each platform. Can you talk a little bit more about that? I'm a little fuzzy on what you were doing. Next.
Yeah, yes. This is about when during the processing, during the mission life cycle, Sometimes it happens that one drone can fail to achieve the mission. So it depends. It can fail because we don't have enough resource to continue, or sometimes if it happens that we have a collision or we detect a crash or some problem. In this case, don't forget that we have a master drones that receive information in real time on the status of the drones and also on the progress of the mission performing locally in these drones. And every time that we progress iteratively, we send information about the feedback of the action performing in the previously. And when the drone receives information, how it classified this? We have here three kinds of priority. The first job is about the useful job that we need for the planning. Sometimes is it about the covariate path planning or the path planning algorithm, because we need this first. If we want to make a survey mission, we need first to fly, and we learn another job for the object detection, something like that. But this is the first one to classify. So we have to understand which kind of priority is it first. After that, we will now make the FIFO priority. By FIFO, it means that the first drone which file will be the first drone, the first task from this drone that will achieve in the first positions. So here, the first, how to detect the first drone, it depends on the last information that we receive. The last one, if the two drone file, for example, we make that if this is filed for the first time, the time that it will receive information will be higher than the time from the previous drone. It means that this will be the drone that we have to process this information firstly. And if we suppose that we have just one drone available, the master drone will look for the drones, another drone that is available to achieve the missions. And sometimes we have, so it depends on the mission. So we have some land point that we generate sometime when we progress in the mission, so that if we have a break, we can continue from these land positions.
Are you doing any kind of when that master gets it and says, okay, hey, I need to give this task to somebody else, are you doing any kind of heuristic for making sure that it's going to one of the followers that we is closest to that necessary task, so that it doesn't get assigned to somebody who's maybe on the complete opposite side of the map that has to fly all the way back over to service it?
Mm-hmm. No, this is not yet implemented.
It's fine, I'm just asking.
Okay. But, so I don't know if, but if we have a lot of processor, we can achieve this kind, because each processor is, here we consider a ROS node as a set of CPU and a set of resources that will use this to allocate. So I don't understand exactly your question.
Yeah, I guess I'm getting confused. Again, it goes back to your concept of what you call a task. And I think that's the right answer.
We have a mission.
Yeah, we'll talk after this.
Okay.
I'm interested in protecting a swarm like this from an adversary taking control. There's so much communication going on. Have you thought about trying to build in encryption in the baseline so that you've got secure communication between the swarm?
No. Don't have secure communication for a moment.
Ross have the ability, if he's using all Ross messaging for this, they have the ability to turn on encryption
But the communication here is not secure for the moment. Okay, so another question.
So the scope of your talk is very broad, very long. How many developers do you think it's going to take to fully realize this?
What?
In your team?
In our team?
Yeah. How much to build on all this infrastructure?
So I worked for around 1 year on this project. It's dedicated for 3 years, but we plan to have some people to join us. And for me, I'm working exactly on the coding part, but we have another guy who is working on the hardware part about the design of the swarm. This is why we have a swarm with the same concept, and we use the Autopilot concept because it's more dedicated for the scientific community. Okay. And so we are open because is it an open project? And so it will be very interesting. We have some people who would like to join us to contribute to the investment of this project. For the moment, is just in the first step, but we just step some little bit with a simple function, but in the future we plan to build a dedicated environment with the capability to embed some complex mission that involve many interaction between different kind of drones. Okay, so thank you.